Okay, for this first question, you are asked to do a free body diagram for the block on the table. And I encourage you to go back to the skill builder for this module and review that free body diagram. But just to kind of give you a little bit of a hint, I'm actually going to go through this. Notice we've got a list of, let me put my marker on here. Notice we got a list of different forces. And the question is, which forces would be at play if we have just a block at rest on a table? Obviously, one choice is none. We know that the block is not moving. And we know from Newton's first law that an object at rest will remain at rest unless acted upon by an outside unbalanced force. So almost always there are forces acting. It's just a matter of the fact when something is not moving, it doesn't mean there are no forces acting on it, but that the forces that are acting on it are somehow balanced. They're not unbalanced, they are balanced. So we can actually eliminate none. This is a block. And one thing we know is that it does have weight, and that's what that's what the force of gravity is all about. So usually I'm going to just draw my block over here. Try to draw these blocks. So there's a block. The earth is pulling on that, and I'm going to put it on a table. There it is. Normally the way that the weight of the block is represented is by an arrow pointing downward toward the center of the earth. And that length of that arrow quite often has to do with the weight of the object. So the heavier the object, the longer we would draw that arrow. But the force that we represent weight with is just a downward pointing arrow toward the center of the earth. Now, that next one is normal. But let me see if I can change. I'm going to change colors here just for fun. So we'll do the normal force next. Normal force has to do with when you've got, we know that block is not crashing down toward the center of the earth. There's a force acting downward, and yet it's not moving downward. That tells us that that force must somehow be countered. And it's countered by the normal force. The fact that that block is sitting on a table, and the weight of the block is smushing down on the surface of that table. And just like when you put an object on, put a bowling ball on a bed, the springs will compress to a certain extent, but the bowling ball doesn't crash down through the bed. It eventually comes to rest. Not because its weight has gone away. The earth is still pulling on that bowling ball, but the springs compress just enough that they exert enough upward force to balance the weight of the bowling ball. Same thing happens with the atoms of the table. They get squished just so much, and they eventually exert enough force upward to balance the weight that's pushing downward. So notice I've drawn that length very carefully to essentially be the same as the weight. Okay? All right, let me change now to a different color for friction. I'll go purple. So in the case of friction, normally if my box was sliding to the right along this table, it would be rubbing. The bottom of the box would be rubbing against the top of the table, and there would be a force to the left. But notice that in this case, our block is just sitting there. It's not moving. So you may think twice about having friction as a possibility here. Applied force, so that was friction. Applied force, I'll do kind of in a peach here, is if we were pushing or pulling on the box. But notice again, the wording, okay, and decide whether that's an appropriate choice here. Let's do air resistance. Air resistance, right? Run down the hallway, wherever you get up out of your chair and start running. What do you feel? You feel you are hitting air molecules, right? You're knocking them out of the way. You're knocking them in the direction that you're moving, but they are knocking against you, and that's what your nerve endings are feeling. So air resistance, kind of like friction, tends to oppose motion. So if this box was moving to the right, it would be smacking into air molecules, which would be exerting a force to the left. However, again, remember, is my box moving? And is it appropriate to use air resistance in this case? Spring force, or the last two really are not at play here. I'm just going to lump them together. Because, again, we're not pulling on the object. If we had a rope attached to the box, which we do, but if we were actually pulling on it, then we would consider that a tension force, because the rope or the string is what's applying the force to the box. But in this case, it's just sitting there. So that pretty much answers that. So going through all that, you should be able to choose which are the appropriate forces at play in this situation.